Welcome to an introduction to the simplex method. In this lesson, we'll solve a standard maximization problem using the simplex method. A standard maximization problem is a problem where all of the variables are non-negative and all the constraints have this form here where they're less than or equal to n and n is non-negative. I outlined 9 steps to apply the simplex method for standard maximization problems. We'll go through each step looking at a basic example. But before we do this, I do want to define active and inactive variables. Active, or basic variables, correspond to columns that contain only one and non-zero entries. Inactive, or non-basic variables, correspond to columns that don't contain only one and non-zero entries. This is important because when applying the simplex method, we can look at the completed tableau to determine the value of the active variables. All of the inactive variables will be equal to 0. So to keep track of the active variables, we label each row with the name of the corresponding active or basic variable. If we didn't do this, we could determine them at the end, but I'm going to keep track of them as we go. So here's our standard maximization problem. We have the objective function we're trying to maximize, and we have our constraints. Notice how the last two just confirm that x and y are non-negative. We won't be using these to perform the simplex method. So step 1, we want to convert these first two inequalities to equations using slack variables. So if 2x plus y is less than or equal to 5, there must be some value which we'll call s, so we can make the left side equal to 5, which means we could write an equation 2x plus y plus some value s would have to be equal to 5. Now leaving some space here horizontally, because we'll have other variables, we want the like terms to line up vertically. For the second inequality, we have 2x plus y is less than or equal to 4. So on the left, we can add another value, we'll call it t, so that x plus 2y plus t would be equal to 4, not less than or equal to 4. And now for the third equation, we'll go to step 2. We're going to set the objective function equal to 0. So looking at the objective function, we want p to stay positive, so we'll subtract the x and y terms on both sides, which would give us negative 2x minus 5y plus p equals 0. Now we're almost ready to set up the simplex table or tableau. Before we do this though, I am going to change the form of these equations slightly. Let's include every variable in every equation. So we'll write the first equation as 2x plus 1y plus 1s plus 0t plus 0p equals 5. Second equation we'll write 1x plus 2y plus 0s plus 1t plus 0p equals 4. Third equation, negative 2x minus 5y plus 0s plus 0t plus 1p equals 0. We'll be using all of these constants in our tableau. So to set up the tableau given here, we first label the columns with the variables used, x, y, s, t, and p. Our first row, again, will be the coefficients from the first equation. So notice how we have 2, 1, 1, 0, 0, 5, 2, 1, 1, 0, 0, 5. Next we have 1, 2, 0, 1, 0, 4. And finally we have negative 2, negative 5, 0, 0, 1, 0. So negative 2, negative 5, and so on. The last thing we want to do is label the active variables here on the left, which would be the columns that only contain 1 and zeros. So that would be S, T, and P. So those are listed here. Again, this is optional, but I do like to show this. Now I should mention that each tableau does represent one possible solution to our problem. This one would just not be the maximum P. For example, we can read off the values of the active variables from the table. The way we do this, looking at this column for S, notice how it's active. So 1s equals 5, so s equals 5. Looking at the column T, 1t equals 4, so t equals 4. And looking at the column P, 1p equals 0, so p equals 0. So remember the inactive variables, which would be x and y, would be equal to 0. So when x and y are equal to 0, the constraints are met, but notice how the profit would be 0. So to find a better solution, we apply the simplex method. So here's the same tableau. Step 4, we want to select the pivot column. This is the column with the most negative number on the left side of the bottom row. If a number is the most negative, it would be the most left on the number line. So notice how this would be the pivot column, because -5 is the most negative number along the left of the bottom row. Step 3, we want to select the pivot row. To do this, we divide each entry in the constant column by the corresponding positive entry in the pivot column. The smallest ratio indicates the pivot row. So we're only concerned about the first and second row. So 5 divided by 1 is equal to 5, and 4 divided by 2 equals 2. The pivot row will never be this last row. So the smallest ratio is 2, which means this is the pivot row. Step 6, we select the pivot, which is the entry in the pivot column and the pivot row. However, the pivot must be positive. Notice in this case it would be positive 2. Now that we have the pivot, we'll be pivoting around this entry. So here's the same tableau. There's our pivot. So now we're on step 7. We perform row operations to make the pivot equal to 1 and the remaining elements in the pivot column equal to 0. So we want this to be a 1, we want this 1 and this -5 to be 0. I should mention that some textbooks don't make the pivot equal to 1, which is okay, but then there's extra steps later. So let's begin by making the pivot equal to 1 by performing a row operation. So we'll replace row 2 with 1/2 times row 2, since 1/2 times 2 equals 1. I've already done this here. I've replaced row 2 with 1/2 times row 2. Notice 1/2 times 1 is 1/2. 1/2 times 2 is 1. Still our pivot. 1/2 times 0 is 0. 1/2 times 1 is 1/2. 1/2 times 0 is 0. 1/2 times 4 equals 2. Next we want this entry and this entry to be 0. Let's do this on the next slide. So again, here's the tableau from the previous slide. If we want this entry to be 0, we could replace row 1 with row 1 minus row 2. Let's go ahead and do that. We'll replace row 1 with row 1 minus row 2. And to make this entry 0, we could take row 3 and add 5 times row 2. Let's perform this row operation by hand. We'll perform this row operation on the calculator. So here we'd have 2 minus 1/2, that's 4 halves minus 1/2, or 3 halves. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1/2, -1/2. 0 minus 0, and 5 minus 2 is 3. Now again, we could do this by hand, but I do want to show how we can do this row operation on the calculator. There's a couple ways to do this on the calculator. I'm going to go ahead and do this from the home screen. So to enter a row, we don't use the parentheses. So I'm going to press second open parenthesis, enter row 3, so -2, comma, -5, comma, 0, comma, 0, comma, 1, comma, 0. Close it. So there's row 3, and then plus 5 times row 2, so open squiggly bracket, 1/2, comma, 1, comma, 0, comma, 1/2, comma, 0, comma, 2, and close it. Press enter. Now it's giving us the decimal form. We want the fraction form, so we'll press math, enter, enter. So we have 1/2, 0, 0, 5 halves, 1/10. We could have just easily done that by hand, but when there are a lot of fractions involved, using the calculator is a nice way not to make a mistake. Now when performing these row operations, notice how t is no longer active. This column no longer contains 1 and zeros. The new active variable would be y. So we replace this t with y. Another way to see this would be to look at the row and column of our pivot. Notice how it's in row t and column y. So t is the exiting variable and y is the entering variable. So we replace the t with a y. Now take this tableau on to the next slide. Step 8 says repeat by identifying the most negative entry on the left in the last row, but there aren't any, they're all positive, which actually means we're done. Step 9, once the left side of the last row is all non-negative, the solution can be found. The value of each row variable or active variable is equal to the rightmost entry in the row. All inactive variables equal 0. So again, looking at the tableau, notice how S is active, which means 1S or S equals 3. And looking at the column Y, Y is active, it's also labeled here, 1Y equals 2. So we know that S equals 3, Y equals 2, and also P is active, P equals 10. Which means the maximum of P under these constraints is 10. Remember, all inactive variables are equal to 0, so t equals 0 and x equals 0. So to summarize, we can say the maximum of P is 10 at 0, 2. Now this is a very straightforward example. Many times we do have to repeat the process because after pivoting once, we still have negatives on the left in the bottom row. Now if we compare this to how we solved a similar problem using linear programming, we would have graphed the feasible region on the coordinate plane. Because our constraints are inequalities in two variables, we would have found the vertices 1, 2, 3, 4, sub those values into P, which I've shown here. Notice how we get the same solution. The max is 10 at 0, 2. When we apply the simplex method, the algorithm begins at a vertex, let's say here, and moves along the edges of the polytope until it reaches the vertex of the optimum solution. I hope you found this helpful.